Hi, I'm Kevin, and I'm an astronomer at Caltech studying exoplanets, planets that orbit stars beyond our solar system. These days, many of us are mostly at home and limited to taking walks around our own neighborhoods. I grew tired of exploring my own neighborhood, so I decided to explore the much more interesting local stellar neighborhood. I built this model using things I found around the house, and you can too at your own pace following the tutorial on my website linked below. All you need is paper, string, tape, scissors, a ruler or measuring tape, and a pen. I'll leave the model making to you, but what I want to talk to you about here are some of the reasons why our local stellar neighborhood is so fascinating, and hopefully this piques your own curiosity about our stellar neighborhoods. Just to note, this is a scale model, which is representative but not completely accurate for a couple of reasons. First, the star sizes are all scaled relative to the Sun. In this model, our Sun has a diameter of 1 inch, or about 2.5 centimeters. The sizes of the stars are accurate relative to each other, and their positions within the model are also accurate, but the positions are not accurate relative to the sizes of the stars. If we took our 1 inch diameter Sun and put it near the geographic center of the contiguous United States in Lebanon, Kansas, our closest neighbor, Proxima Centauri, would be about 450 miles or 725 kilometers away near Minneapolis, Minnesota. That's a much more difficult model to construct. Let's start with the Sun. We have a lot to be thankful for about the Sun, since without it, none of us would be here today. In the somewhat confusing classification scheme astronomers use to categorize stars, our Sun is a G-type star. This means that the Sun has a surface temperature of about 5,800 Kelvin. I won't talk more about our Sun, but it is intriguing in its own right, and a lot of what we know and can learn about other stars depends on precise knowledge of our own star. Our closest neighbors are in the Alpha Centauri system, a little over 4 light years away. 1 light year is the distance it takes light, traveling at about 300,000 kilometers per second, to travel in 1 year. Light we observe from stars in the Alpha Centauri system took over 4 years to reach us. This star system has 3 stars, Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. Alpha Centauri A is nearly identical to the Sun, but is just a little bit bigger. Alpha Centauri B is slightly cooler and smaller than the Sun, and astronomers classify it as a K-type star. Proxima Centauri is very different from the other 2 stars. Like I mentioned earlier, it is actually the closest star to our own solar system, but it is gravitationally bound to the other 2 stars, Alpha Centauri A and B. Proxima Centauri is what we call an M-dwarf, or a red dwarf, due to its reddish color. It is much smaller and much cooler than the other stars, burning at about 3,000 Kelvin. In 2016, a group of astronomers discovered a planet slightly larger than the Earth orbiting Proxima Centauri. In 2019, astronomers identified another possible planet around Proxima Centauri that's a bit bigger and a lot more massive, but more data are needed to confirm this planet. Most of the stars in this model are like Proxima Centauri. They're M-dwarfs, including Barnard's star, Wolf 359, which also has 2 known planets, Lilandi 21185, Luyten 726-8A and B, and Ross 154. These stars are typically about half the mass and radius of the Sun, or smaller, and they comprise about 70% of all of the stars in our own galaxy. While stars like our Sun have lifetimes of about 10 billion years, some of the smallest M-dwarfs may be able to live for over 1 trillion years. While M-dwarfs are pretty cool, brown dwarfs are even cooler. Lumen 16A and B and WISE 0855 are brown dwarfs. These objects aren't actually stars because they are too cold to fuse hydrogen in their cores, but they are still too massive to be considered planets. Even though the Lumen 16 system and WISE 0855 are the 3rd and 4th closest systems to our solar system, they weren't discovered until 2013 and 2014. Since they are so cold, about 1300 Kelvin for Lumen 16A and B, and about 250 Kelvin for WISE 0855, they emit almost no light at optical wavelengths where our eyes and most of our instruments can see. These brown dwarfs were discovered using data from the Wide Field Infrared Survey Explorer, which is a space telescope operating at infrared wavelengths, where brown dwarfs emit most of their light. You definitely can't see brown dwarfs without special equipment, but you have almost certainly seen Sirius, since it is the brightest star in the night sky. Sirius A is an F-type star, about twice as massive as the Sun, and burning at about 10,000 Kelvin. The Sirius system is relatively young compared to our Sun, at about 250 million years old. In our scale model, Sirius B is extremely tiny. It is a white dwarf star, about the same size as Earth, but just as massive as the Sun. Sirius B used to be a lot bigger, about 5 times more massive than the Sun. Big stars less than about 8 times the mass of the Sun quickly burn through their hydrogen in their cores and then expand and become red giants. Eventually, these red giants eject the material in their outer layers out into space, creating a beautiful planetary nebula and leaving behind an Earth-sized carbon-oxygen core. And there you have it. This has been a very brief tour of our local stellar neighborhood, so I will leave it to you to go build your own scale model and learn more about the fascinating neighborhood around us. Bye, and stay safe.